All right, so we've learned a lot about SN1, we've learned a lot about SN2, but up until now we haven't really talked about how do we know which one's going to happen. And essentially where we need to be is we need to be able to look at an alkyl halide and a nucleophile and say, that is going to be SN1, that is going to be SN2, that is not going to react at all. Those are the things that we need to be able to figure out based on what the alkyl halide is and what the nucleophile is. We can kind of break it down like this. One of the most important points is, what is the alkyl halide type? And one thing that we talked about a few pages ago is that, actually I think it was just last page, is that primary alkyl halides, they can't form carbocations. So if they can't form carbocations, that means they can do no SN2. Sorry, no SN1, because SN1 requires a carbocation. So primary alkyl halides undergo SN2 or no reaction. No reaction. So SN2 or no reaction. We're going to get a bit more into that in a minute, but essentially they can't do SN1. We can say that for sure. Tertiary alkyl halides, they are so sterically hindered, right? They have all those big carbon groups around that sigma star orbital. The nucleophile can't get to that sigma star orbital, so they can only do SN1 reactions. Only SN1. And they always do SN1 because they're too sterically hindered for SN2, and essentially they can only, if it's between SN1 and SN2, they can only do SN1. And they form a really stable carbocation. So we'll say that too. They form most stable carbocation type. They form the most stable carbocation type, and too hindered for SN2. There's no access to that sigma star orbital. Okay, so why did we list primary as SN2 or no reaction? Well, it turns out that it has to be a reasonably strong nucleophile to do an SN2 reaction. Essentially, a primary alkyl halide with a weak nucleophile is essentially just not going to do anything. So essentially we can break that down here then to SN2 with a strong nucleophile and no reaction with a weak nucleophile. So what's a strong nucleophile? What's a weak nucleophile? We're going to get there in a minute. But now we're going to talk about secondary alkyl halides. So essentially, secondary alkyl halides are the only ones that can do either one. They can do either SN1 or SN2. And we'll kind of separate them out down here. So essentially, they would do SN1 if they had a weak nucleophile, and they will do SN2 if they have a strong nucleophile. So essentially, the things that are confusing would be are all related to nucleophile strength at this point, right? Tertiary, they can only do SN1 because the nucleophile can't get to their sigma star. So it's just like, boom, always SN1. Primary, they can't form an unstable primary carbocation, so their only option is SN2. But again, they need a strong nucleophile to do that, or they will do no reaction. So really what things are coming down to is is classifying nucleophile strength. Do we have a strong nucleophile or a weak nucleophile? And that's what we're going to talk about in just a moment. All right, I need to get some more stuff into my notes. Apparently, I don't have a perfect note packet out there, so this part is not perfectly done. But essentially, we're talking about nucleophile strength, and we have strong nucleophiles versus weak nucleophiles. If I had a perfect note packet, this would already be on there somewhere. And we'd probably fill in the blanks below it, so we wasted 30 seconds. So not a big deal. All right, here we go. So essentially, strong nucleophiles. What do we compare nucleophiles to? Bases, right? A strong base is a strong nucleophile. And a strong nucleophile is anything where the conjugate acid, actually, yeah, let's put it in the form of the base. So a base whose conjugate acid has a pKa greater than or equal to 5. So what does that mean? Let's look at some nucleophiles. So actually, let's talk about weak. So weak is just that cut off the other way, right? It's a base whose conjugate acid has a pKa less than 5. Okay, yeah, so now let's look at some examples. So what if we had a nucleophile like this one? So we have a nucleophile, it's like the only atom here that has electrons to give to an electrophile is the oxygen, so this oxygen is our nucleophile. Well, what does its conjugate acid look like? So yeah, let's classify some nucleophiles over here. And again, this is the reason why we really need those pKas up in our head. We can't look at a piece of paper every time for this kind of thing. But the conjugate acid of this would be H2OCH3 plus. So what would its pKa look like? We don't have the pKa of that exactly, but what's the most similar pKa that we do have? All right, who's going to answer that? No one, because I'm alone in my office. The most similar pKa that we would have is H3O plus. Why is that? Well, it's an oxygen with 3 things bonded to it, and a lone pair, and a positive charge. What is that one? It's an oxygen with 3 things bonded to it, and a lone pair, and a positive charge. So very similar, right? So they're going to have similar pKas. The pKa is negative 1.7 of hydronium ion. It's going to be really similar for that as well. So this then must be a weak nucleophile. What about its deprotonated version? So OCH3 minus. Is this strong or weak? Let's look at its conjugate acid, HOCH3. This pKa is going to be really similar to another one on the list. One thing that's on the list is ethanol. This pKa is 16. Methanol, just with a CH3 instead of a CH2 CH3, is also going to be around 16. So this guy's conjugate acid has a pKa greater than 5, right? Which means it's a strong base. So this guy here is a strong base, a strong nucleophile. Let's do another one. NH3 by itself, okay? What's its conjugate acid look like? It looks like NH4 plus. This is another one that was directly on that pKa list. That has a pKa, I mean, actually, it wasn't directly on there. I added it to there because I knew that it would be helpful. And it has a pKa of 9. So this, just like this one, is a strong nucleophile. So some people say, like, oh, strong nucleophiles, they're always negatively charged. They're not always negatively charged. Both of these are strong nucleophiles. Essentially, nitrogen that is neutral is a strong nucleophile because its conjugate acid's pKa is pretty high. So that's the best guideline that we can get for strong versus weak, and that will allow you to figure out if things are going SN1, SN2, or no reaction in some cases. So we're going to do some of those practices on the next page.